welcome to the St. Louis Zoo. I'm Jim Jordan, Curator of Education, and this is the last of our science seminar series at the zoo this year. We've had an incredible turnout, and since this is part of spring break, I commend all the students who are here on their vacation. But normally we would have more students, I think, if it wasn't for spring break. We will be putting together next year's schedule sometime later in the spring, and you will either receive e-blasts or a mailed brochure if you've signed up on our list. And a little bit, we'll send around some clipboards. If you've already signed up in the past, no need to repeat it. But if you'd like to find out about the science seminar for next year, plus a lot of other free science programs throughout St. Louis, we encourage you to sign up. I just want to mention one thing coming up later in June at the zoo that you might find intriguing. The last few years, they have had an event nationwide called National Pollinator Week. And many of you have heard about the crises that some of the native pollinators and bees have faced. Well, we're going to have a variety of programs, and one of them on Tuesday night, the 18th of June, we're going to have a pollinator dinner. And it's going to feature all foods by pollinators. We'll even have some honey wine and honey tastings, plus a lot of information and booths and things that you can learn about pollinators. So information will be coming out on our zoo website as far as price, and it's going to be very, very reasonable for the dinner and everything. So we encourage you to check that out if you're interested in a fun evening. So given that, hope to see you all back next year for our science seminar series, and I'm going to turn it over to Rose Jansen with the Academy of Science.
Good evening. I'm Rose. I'm with the Academy of Science. And for those of you who are not familiar with us, I know a lot of you are, so pardon the little blurb about the Academy. I'm going to let you know a little bit about who we are and what we do. We are one of the area's oldest not-for-profits. We've been around since 1856, and we have a long-standing mission to advance the public understanding of science and inspire the next generation of scientists and science advocates. And we continue to celebrate more than 150 years of community service by offering a broad range of free and low-cost public programming, collaborative seminar series, and trips and tours that highlight science at venues throughout the region. And you can find more information on the Academy and our community-wide events and programs by visiting our website at www.academyofsciencestl.org, or you can pick up some of the literature just outside the auditorium on your way out. And as Jim said, if you'd like to receive e-notification of upcoming Academy and St. Louis Zoo public lectures and events, there will be e-news sign-up sheets that'll make their way around the audience, and we don't share your name with any other organizations. This is the final seminar in the 0809 series, as Jim said, and we are in the process of putting together next year's series. So again, if you sign up on the sheet, that will make their way around the audience. Or if you're already on our list, you'll receive a brochure or email notification of the 09-2010 series. And with that said, I'd like to introduce tonight's speaker, Dr. Pratim Biswas. Dr. Biswas earned his Ph.D. from Caltech. He is a fellow of the Academy of Science St. Louis and is currently the Stifel and Quinette Jens Professor and Chair of the Department of Energy, Environmental, and Chemical Engineering at Washington University in St. Louis. He has been with the university since 2000 when he was hired as the director of the Environmental Engineering Science Program. Under his leadership, the Department of Energy, Environmental, and Chemical Engineering was created in 2006. He also played a lead role in the creation of the Energy and Environmental Initiative at the university and is the director of the McDonnell Academy Global Energy and Environment Partnership, which is a consortium of 25 global universities and corporate partners, all working together in energy, environmental sustainability research, education, and operations. Dr. Biswas's research interests include aerosol science and engineering, nanoparticle technology, air pollution control, and energy and environmental nanotechnology. He is director of the university's Aerosol and Air Quality Research Laboratory and also serves on the steering committees for both the McDonnell International Scholars Academy and iCares, the International Center for Advanced Renewable Energy Sustainability. So he is a busy, busy man. We are very pleased to have Dr. Biswas here with us tonight to talk about the Energy Environment Nexus, Engineering Clean Energy for the 21st Century. So on behalf of the Academy of Science and the St. Louis Zoo, won't you please welcome Dr. Biswas.
Hope you can hear me at the back. It's a great pleasure to be here on a nice, warm spring day. And I'd like to first thank the Academy of Science and the St. Louis Zoo for inviting me to speak to you. As Rose mentioned, I'm an aerosol scientist. Aerosol basically is a little tiny particle. It could be that pollen grain which helps pollinate the next flower, or it could be a nanoparticle, or it could be a raindrop that comes crashing down. So we use that knowledge of fine particles that are suspended in a gaseous medium to study a variety of different systems. Today I'll be talking about the energy and environmental nexus and how this is a global challenge problem, and I really, the initial part might sound a little daunting from what I'm going to say, but that's where science and technology has to really step up and come up with the solutions. So just to get started, I don't know if this shows too well. If you look at this, these are images of the globe, and they're juxtaposed nighttime images. So these are all nighttime images. Obviously, when it is nighttime here, it's daytime on this part of the globe, but we have juxtaposed nighttime images taken by satellite, and you can see how they light up. So if you look at the United States, we are somewhere there, quite well lit up because there's a lot of energy being consumed, electricity being consumed, electrical energy to light up bulbs like this or like the projector bulb. And you can see there are certain parts of United States which still remain dark, and we are of course very well developed here, but the population density is very thin in these regions in the upper Midwest and so forth, and that's why not much energy is being consumed. You can look at places like China, which are now lighting up, India lighting up, Europe of course, very dense population. But then there are certain parts of the globe, you cannot see it, Africa, maybe Latin America, which is populated but still remains dark. So there's a thirst for energy, and a picture like this, of course, tells us a lot that as these people start lighting up because they want to consume energy, and you can see that the need for energy is going to be quite significant. So with that, this is the outline of my presentation. As I said, I'll talk about global energy issues. To lead off the talk, I'll take you and see how the future looks like and what we need to be doing, and then try to sort of indicate that there is a great need to come up with clean energy solutions, and also talk a little about Washington University and how scientists there are working together to come up with some of these solutions. So first, before I get going, because it's a mixed audience, and please pardon me if you're very familiar with all these terms, I just thought I'm going to give you a little walkthrough in terminology. Firstly, what is energy? It's the capacity, or the word has, of course, a Greek origin, energia. It's the capacity to do work. So energy is the capacity to do work. We quantitate it. We measure it in joules. We can also measure it in calories. We take our food. If you look at a canned food label, it will tell you how many calories. That's basically the energy. You eat it, and you can then begin to do work. A machine does work for us, so the capacity to do work is called energy. And I'm going to use the metric system of units or the international system, so we call that joules. And then there's another term, power, because the rate at which I do work, or the rate of doing work, basically is energy divided by time. There's a certain time period, and that is referred to as power. We measure that in watts, of course named after James Watt, the inventor of the steam engine. And then there are terms like kilowatts, megawatts. Horsepower was another unit of power, because in the good old days before the steam engine was invented, there were horses that provided us the capacity to do work and the energy, and so we measured it in horsepower. But we are going to use the international system of watts. 1 watt is 1 joule per second. As I said, it's energy per unit time. And of course, we want to get a better understanding of these. These are units. So I can look at something very common, a light bulb, which all of us should be familiar with. There's a whole bunch up here in the front row. One light bulb typically, let's say, is 100 watts, right? The power rating of a bulb is 100 watts, which means it uses up 100 joules of energy every second. As we go along this talk, I want you to get a feel for these numbers. I leave it on for 10 hours, right? We work 10 hours a day, let's say, 100-watt bulb. Then watts multiplied by time. Power, when I multiply it by time, I get the energy. And so I take a 100-watt bulb, I leave it on for 10 hours, and that's watt times hours, right? That's the amount of energy. And that's 1,000 watt hours, which is called 1 kilowatt hour. So 1 kilowatt hour of electrical energy is consumed by this bulb, which I leave on for 10 hours, a 100-watt bulb. It could be in our home. Sometimes we don't turn our lights off. That's the amount of energy. The first thing to see is we always say, hey, I just left it on. How much does it cost me, right? I'm leaving this 100-watt bulb on for 10 hours. I consume 1 kilowatt hour of electrical energy, and you'll be surprised. Electricity in this country, especially in St. Louis, is extremely cheap, low cost, right? It just costs me about 10 cents. And maybe that's why our behavioral patterns are such that whether I use the lamp or not, I don't turn it off. It's less than 10 cents that I have to pay for it. But I want to bring in that environmental connection and also address the issue of our behavioral aspects as we go along. I won't talk much about it, but it's important to note. And then I might not have just one light bulb. I might have 10 light bulbs. Then it's 1,000 watts. That's called 1 kilowatt. These are basically multiplier units. 1,000 kilowatts becomes 1 megawatt. We want to have a scale for the megawatt, right? You can imagine this to be 10 light bulbs, 1,000 watts, but 1,000 of them, 1,000 kilowatts make up 1 megawatt. 1,000 megawatts make up 1 gigawatt, right? A modern coal-fired power plant, several of them around St. Louis, can produce 1 gigawatt of power, right? So that's, again, I want you to get a feel for numbers. And then 1,000 gigawatts is 1 terawatt, right? So this could be 1,000 modern coal-fired power plants or energy-generating plants, and that's 1 terawatt. So you get a feel, it's actually 10 raised to 12 watts. So these are large numbers, and just to get a feel, you can go all the way back to a single light bulb, approximately 100 watts if it is nice and bright. But you can then see what a gigawatt is, a megawatt, and a terawatt. So remember, 1,000 gigawatts is a terawatt, or it's 10 to the 12 watt. So this will come up quite often in the presentation, so I'd like you to pay attention. Okay, what's new in this energy sector? We all have been consuming food. We want to generate energy. We want to light up our bulbs. It's been around at least for, I talked about James Watt. I think he was around 200 years ago, or at least 150 years ago. What is new? There's something called the energy equation. So I need to have a source, a fuel. Typically, many of us drove here. We used a fuel which we combusted to provide the energy, which pushed our car and brought us here. So we need to know about fuel economics. There's a cost to the fuel. There are also reserves. Do I have unlimited quantity? There's something called energy security. We hear that a lot. Are we safe here in the United States? Can someone turn off the faucet and there goes all my gasoline? Maybe. It comes from the Middle East, so there are energy security issues, right? Of course, the sun also provides us energy, and the sun is not as selective, shines all over the globe at certain times of the day. And then the environmental connection. We hear a lot about carbon dioxide and the connection to global warming, and there are many other environmental pollutants which we have to be cognizant about. So these things have been around for a long time. In fact, when I started my education, graduate education, energy was a very topical issue, but somehow you notice in the past they come and go. Research and development was in prime, some of you who were around in the 70s, but it just waned and we didn't hear about it. So there's also this connection to the political scenario, the political will, and also the energy equation, I think, plays a role because that controls it. But now things are different. It has resurfaced. If you turn on your television, you'll hear energy mentioned umpteen number of times. There's a change in administration here in the United States. They're making a big deal out of energy. So clearly it has resurfaced. But it's the prediction that it's not going to wane is very important, and that has got to do with the terms of this energy equation. And I just list two of them. One is this carbon dioxide issue. Clearly it was there also in the 70s, but the recognition was not as clear, right? The scientists were still debating, but now it is very clear. Any fossil fuel, when you use it, gives us energy, but also gives us carbon dioxide. This results in a global climate change, which is a very complex issue by itself. People don't understand it, but impacting all of us on this globe. So we really need to understand this, and it's linked to all our energy production processes. Now, the emerging and growing economies in the developing nations is another factor. If you look at the population growth, there are only certain centers of very few countries where it's growing rapidly. India, China, parts of Asia, and also in the United States, actually, there's growth in population because of immigration and so forth. But the developing nations, it's quite a remarkable increase. So this makes us thirsty for energy. Recall that picture of the globe with all the lights still needing to come on. So that's why this has resurfaced. We hear a lot about it. The young folks in the audience, I think you have a 30-year career ahead of you or longer, maybe 40 years. Some of us feel that this is going to be important for that time scale. It's going to take time to come up with solutions, as I'll soon point out. Okay, global warming, I don't want to talk too much about it. It's very well accepted now that the average temperature of the globe is going up. It's because of these greenhouse gases. I just wanted to point out that this is a very complex problem. Greenhouse gases come from all the cars that we drive around. It comes from our energy production processes. But being an aerosol scientist, I wanted to throw that in. We also release fine particles into the atmosphere. When we drive our cars, the fuel doesn't burn as well, so there are small particles. Some of you might know them as soot, but there are particles of different kinds. These actually cause global cooling depending on the type of particle. So extremely complex. And then you can see if there's a sudden release of particles due to a volcano. There's a volcanic eruption, the temperature comes crashing down, again relative scale here, because fine particles that are emitted from volcanoes cause global cooling. So very complex thing, but no doubt that the average temperature is going up. Carbon dioxide concentrations are going up. It's well understood that this is true. Now many people point that carbon dioxide concentrations going up are due to anthropogenic activities. That's activities of humankind because we are thirsty for energy. We are using more fossil fuels, while the direct impact still may be debated, and as I indicated, is very complex. But there's a clear understanding now that global warming is real. and it's having tremendous impact. And of course, we here in the United States have been major contributors of greenhouse gases, and we have to address it too, but it's a global problem. That's probably my only slide on global warming. Let's talk about the other factor in the energy equation, that of world population growth. You can see industrial countries are beginning to flatten out, and these are of course projections after 2010, but pretty much it has agreed, and these are very realistic projections. So by 2050, some of you are going to still be around. The population today is 6 billion people, right? It's going to go nearly double to about 12 billion people on this planet, our only home planet Earth. Okay, as these people grow, of course they have to feed themselves, they have to be productive, they're going to be energy consumers. And there is a direct correlation. If one looks at energy consumption and global population, there's a very strong correlation. So the blue line is the global population, and as I indicated, it's going to shoot up all the way to about, this is till 2030. In 2050, it's going to go up to, as I said, 12 billion people. Quite realistic estimates because of the projections which are realistic. At the same time, energy consumption also has to keep going up because these people are going to survive on the planet and so forth. So just to look at numbers, today we consume about 14 terawatts, 2009, soon to be 2010, about 14 terawatts. Remember what a terawatt was, right? It's 1 terawatt is 1,000 gigawatts. One of those plants next to St. Louis produces about 1 gigawatt. So you can see to have 14 terawatts, you need many, many of these power plants going at the same time. And we are doing that today. But look at the projections, 24 terawatts in 2030. Let's look at 2050, 30 terawatts. Let's just project to 2050. It's a nice round number. So the question is that 16 terawatts more than what we are consuming today, right? It's from 14 all the way to 30 terawatts, that's 16 terawatts. So the first question I'm going to ask is, how much is the 16 terawatt? You have a feel. Look at your little light bulb. So this is humongous. It's a huge number, 16,000 gigawatts, right? So to get the 16,000, and this is additional, because people are still going to be here, so it's from 14 to 30, so this is the additional 16 gigawatts. 16 times 1,000 gigawatts, right, because a terawatt is 1,000 gigawatts, or 16,000 new power plants. One power plant, recall, produces 1 gigawatt. 16,000 new power plants. Of course, we have 40 years to do that. So I put up my next bullet. We have 40 years, so let's not panic. We can take care of it. But let's try to do some very simple arithmetic and do this. 16,000 divided by 40, that's 400 every year, right? We know that 1 year has 365 days. If you're lucky, it's a leap year, 1 additional day. But you have to make more than 1 every day. So we better get started now if all these projections are correct. Okay, so I hope you begin to understand the magnitude of the problem by every means that we look at this. Whether the numbers are off by a certain factor, this is really quite humongous a number to deal with. A clear global challenge that we face, right? And of course, we need technological breakthroughs. And of course, you can say I can build a power plant which maybe generates 10 gigawatts 10 years later. I can do that. Those are incremental changes. We need a transformational change and what we call a scientific and technological breakthrough, literally, right? Now, don't lose hope. There is the sun. Just to again get a perspective, the sun's shining, and hopefully will keep shining. It provides us 174,000 terawatts. This is on our planet Earth. This is what we get as a total. Obviously, it's distributed all over the globe. That's one. It's nighttime now. It's providing us 0 watts Forget terawatts, it's providing us 0 watts now. So it's cyclical, the day-night cycle, but I want to consume energy. My lights are on now. So there are several challenges here, but we just keep this in mind. And then keep those terms of the energy equation, the global warming problem, the global climate change, and all the associated impacts. I want this to be environmentally benign. That's why we term this a global challenge problem, and let's see what we can do about it. As I said, we always look to history, right? And not too much ago, there was this scientist, Paul Ehrlich, at Stanford University. He wrote this book called The Population Bomb. He looked at population growth, actually predictions then, and pretty much this has been population growth. As I said, we are about 6 billion people today. In 1968, he said that even in 10 years, the population is going to increase. Where will we get all the food from? Forget energy. Of course, we need energy to produce food and so forth. They are interconnected. But he was just talking about survival of people and where are they going to get all this food from. And he said that millions are going to start dying, right? Not millions, hundreds of millions of people will perish. This curve has agreed with what has happened. What has not happened is hundreds of millions of people haven't perished. That's why I call the marvels of technology. Maybe I should have said biotechnology. And we are all familiar with the Green Revolution and the invention of chemical fertilizers. Both individuals associated with this, or several individuals, have won Nobel Prizes. And clearly this was a transformational change. You can see food production shown here in red, how it met the challenge. And so there's always hope. It prevented starvation and literally fed the world. Now you might say there were environmental consequences of this. Clearly that every technology has that. Our awareness is now increasing. If that were a parameter in the equation, the environmental connection, we would have even tackled that. So technology is also used to tackle challenges or environmental challenges, but this is a remarkable lesson. Of course, he proved to be wrong, and thankfully so, but it was because of the marvels of technology. So this is just a brief step back in history, and there are many such examples, but clearly transformational changes which made an impact. Okay, let's now move on, and I want to move on and take a snapshot of the future. So global energy use by type. Now you look at where are we consuming. Of course, I gave you this 12 terawatt number. This is my only slide where I sort of took from the DOE site. It's in British thermal units, so please pardon me, but 1,000 joules is about 1 British thermal unit, so you can change the scales. But you can see that the fossil fuels are dominating. Fossil fuels are stuff that we typically dig out of the ground. It has taken geological timescales to form them, to create them. So it takes a long time. We can consume them very rapidly, so we cannot replenish them. The consumption rate exceeds the formation rate, which is very slow. And then obviously someday we are going to run out of that because of the simple rate equations. But you look at the renewables, very small percentage. Look at the projections. The projections also indicate that we are still going to be relying on these fossil fuels. Again, keep in mind the energy equation, the global climate parameter, the carbon dioxide parameter. Every time I use this, I'm going to, of course, produce more carbon dioxide, right? So we really have to meet it head on and see what happens. Fossil fuels, the message here, fossil fuels will dominate in our lifetime. Okay, no doubt about that. Let's look a little more carefully at these renewable sources. And I might call all of these renewable. Nuclear sometimes has a question mark. Biomass, amongst the renewables, biomass is the most used because of the use of wood from trees and things like that, again for base survival in the developing parts of the world which haven't caught up. But you can see the increase in solar technologies that are being used in wind. This is a very small fraction. It's just a sliver of the total, but at least the curve is in the right direction. But one must remember that it's, as a whole, all of the renewables are going to produce less than 10% of energy in 2020. I want to show another curve. This is a graph of something called the Human Development Index. This is a United Nations developed index which relates to three things. One is how much money I have, right? So I'm productive, I work hard, I get rewarded with money, which I can go out and use in the market to do all kinds of fun things. So it's the GDP per capita of a nation. The other thing is my literacy level. Do I know how to read a book and have fun? Do I have some basic education and so forth that I can enjoy? So that's also added up in this Human Development Index. The third thing, very important, is how long I live. Right? Different people in different parts of the world live for different periods of time. There have been marvels of medicine that are increasing the longevity of human beings all over. You might say the Green Revolution in terms of biotechnology, increasing food production helped, but that's also included in the Human Development Index. So you might debate, is this index good? But at least three terms which we all relate to and which are important. And these are normalized, so an index of 1, of course, is you're on top of the chart. That's the best you could be. So you look at this index, people in the United States, certain parts, the developed countries, so-called developed countries, are getting close to 1 or close to 1, whereas there are certain parts in Africa where they're really clamoring to climb up. One can, of course, debate, do I want to learn how to read and have a good life, or is that what a good life is? Do I want to have more earning power to do things? These are all debatable issues, more social science issues, but having agreed that this is a well-accepted index, let's say that's true, then these people would be clamoring to come up the chart. Of course, everybody wants to live long, right? So that at least is in agreement, so we want to move up here. Plotted on this x-axis is the electricity consumption. And remember, energy is in kilowatt hours per person per year, right? So this is the electricity consumption. And you might say, is this the right thing to plot against? This curve, as you can see, is increasing. And should I plot it against this? Let's say that, okay, at least I showed you my first beautiful slide taken from the satellite with the satellite images. It relates to somehow to electricity consumption at night in terms of the light, lights that we light up and so forth. So, but let's also say that this is reflective of energy consumption in some way. And you can see that United States has an index of 0.95 or whatever. Germany has the same, but they consume much lower amount of energy. So are we wasting energy here? Look at Norway. They're way out on right field. So there is the concept of energy efficiency. There's the concept of how much I'm using. Maybe I'm not doing it efficiently, and I could be here and be equally happy, provided, again, that index, living long, learning how to read and write, and having enough money is important. So this is one message, right? The other thing is we have to agree, look at India and China. They are clamoring to come up here, at least as much as Germany, for example. And the population base here is so significant that the multiplying factor, clearly we in the United States need to move that way. I don't want to sacrifice my quality of life. Let's make that an assumption. Let's just say that it's longevity. Obviously, I want to live as long as I can. These folks want to also move up the chain. So let's say we need to move this way. These folks need to move that way. But the population base here is so large that when you multiply by the population, the electricity consumption, or if I say energy consumption, has to be tremendous. So I say that everyone should get HDI, the Human Development Index of 0.9, and I'll be happy with 6,000 kilowatt hours. So right at the edge of this curve, assuming this curve is realistic and we are okay with it, right? So all these guys have to move that way, and all these folks have to move that way, and you can see that I still need 8 terawatts more, 8 terawatts, 8,000 gigawatts, 8,000 more power plants right now today if I want to make everyone happy, again, assuming this is the right index, okay? You can see the global challenge that I face right today if I want to bring in and make everybody equal and happy and so forth. At least in terms of living long, that's a unified goal. So this is a big challenge. Clearly we don't have it. I can't build 8,000 power plants tomorrow. It's going to take me years. Where will I get all these resources from? And so forth. So keep that in mind. Where is all the energy used? We use it in transportation. As I said, we all drove our cars here. We use it in industry to make products. We use it in commercial sector. We use it at home, right? So, and you can see equally distributed. So if I want to push the United States to less energy consumption, I got to look at all of this, including what we do at home. People say, oh, home, we just consume a little amount. True, we don't pay much on a relative scale, but every sector has to receive some kind of attention and some kind of energy efficiency, energy conservation measures. We have to design new automobiles, maybe new fuels, which are not as taxing to the environment and so forth. So this is where all the energy is used. So just to summarize now, and I just want to immediately jump. Firstly, humongous amount of energy needed. Even today, if I look at it, right, we are going to rely on fossil fuels. Let's not just say fossil fuels, let's get rid of it. We can't. I need the energy, okay? And I'm going to need it for the next 50 years. This concept of making it environmentally benign is so critical, especially carbon dioxide and many other things. We need to address it right now, and maybe we can do that. This is also technology coming to play a role. Then we need to begin to look at new sources. We also talk about nuclear. Everybody says, let's go nuclear. The global climate change problem will be taken care of. Remember those 8,000 power plants I need to build, right? And it takes about close to 15 years to get one nuclear power plant online. So it's a tremendous challenge. Move into other kinds of ways we consume energy, maybe in a distributed manner. Can I produce it locally in smaller amounts in a completely benign manner? Can I do things with new fuels, not to rely on fossil fuels, maybe use hydrogen? But the key message is the portfolio is going to be a mixed. It's literally like a grocery bag. It's going to have all kinds of things, and it's going to be a mixed bag of different resources. So that's the message to take. And now let's see, I have at least pointed out the tremendous challenge that we face. How do we tackle and solve this? And that's what I call engineering clean energy solutions. Towards the end of this, I'll tell you a little about Washington University and what's happening there. But we want to look at this. Fossil fuels, can't ignore it. Now is the right operative. I need to begin to transition. I need to look at transformational efforts because of this tremendous issue. Solar, as I said, 170,000 terawatts. Can I begin to tap this more effectively? What are some of the challenges? Never forgetting the environment, because we have our only home, the planet Earth, and we got to continue living in it for several generations. So again, another snapshot, or how does this look in a different form? Where does all the energy come from? Look at United States. Just for electricity production, coal, we use some natural gas, nuclear, these are all small amounts. We spend a lot of energy resources, petroleum-based products primarily, for transporting ourselves. Could we do some things differently, right? You look at the globe, it's pretty much the same. All these other things are a small contributor. Obviously, we want to increase that, but we also have to address what we are doing currently, because we need all this energy. So I'm going to pick the dirtiest of dirty fossil fuels, at least as most people know it, coal, right? It's a large amount located around these regions here in St. Louis and consumed here in St. Louis and our neighborhood. So let's look at coal. And many people call it a four-letter word, and we shouldn't do anything with coal and get rid of it completely. We use the terms, hey, let's use clean coal technologies. Many people say that's an oxymoron. There's nothing what is called clean coal. But let's keep all our parameters in mind, and let's look at the amount of coal reserves globally, 10 trillion metric tons. And as I said, we are using it now. See how well it's distributed. Well, meaning Africa is a low amount in terms of continents, but otherwise well distributed, unlike petroleum and gas, natural gas, which is concentrated in certain parts of the globe. This is more well distributed, if I might use that term well. Of course, you might say Africa has none or a small amount. Australia has a small amount. But otherwise, at least it's better than oil. So that addresses the energy security issue, right? This is an important part of the energy equation. Many parts of the world, and that's why India and China, it's a very low cost and dense energy resource. So climbing up that human development index curve, this becomes readily available. Let's not forget the environmental linkages, and we really have to address that, but it is a valuable resource, and I want to talk a little more about it. Some more facts. China builds a 500 megawatt coal plant every week. They're not going to ask you and me whether they should do it. They're doing it, right? India will do one every other week. So even if we don't do it, these folks are doing it. So even that argument, tells us that we need to pay more attention to coal. And what does one 500 megawatt coal plant do? It burns 200,000 kilograms, right, per hour of coal. Just imagine the magnitude. I told you it's widely available. There's a lot of it, but look how much is consumed. 200,000 kilograms every hour in one plant. And that's also happening in St. Louis, by the way, right? We have 500 megawatt plants. Our electricity comes from burning coal. We are burning coal as I speak here. It's dumping CO2 into the atmosphere, 750,000 kilograms every hour. These are mind-boggling numbers. We are all familiar with a kilogram, right? It's 2 pounds or more. And you can just imagine every hour how much CO2 is being emitted. And 50% of our own electricity here in the United States comes from coal. That amounts to 2 billion metric tons of carbon dioxide. So these are problems we have to be familiar with. I don't want to be sitting in the dark, right? I want to use this projector so I can talk to you folks. What do we do about it? And again, comes back to technological solutions addressing the environmental issues. So coal is widely used globally, great importance to this region, right? But as I said, we need technological solutions. And now let's look at this. There are new ways in which I can burn coal. The key now being, let me just focus on carbon dioxide. We want to tackle this. We want to make sure we are not dumping carbon dioxide back into the atmosphere. There are new modalities with which I can burn the coal. I want to demonstrate carbon dioxide capture. Just imagine the magnitude of carbon dioxide that I have to capture. And then, of course, sequester. I don't want it to go back into the atmosphere. And then, can I treat carbon dioxide as a resource? Does anyone use carbon dioxide? Yes, the beer industry uses it, but it's a minuscule amount compared to the amount that's coming out of a single power plant in the St. Louis region. And now add up all the power plants around the globe, it's a daunting problem. So this is again tells me I need transformational solutions. I can't just do incremental stuff. I need to come up with new ways. I want to tell you what is oxy-coal combustion. So give you another walkthrough in some of these things. The conventional paradigm has been take the fossil fuel, this could be gasoline, mix it with air, burn it, and then start scratching your head. I need to control all the pollutants at the end, and I design new technologies at the end. Can I begin to think in a new fashion, right? So can I look at it as a system? For example, nitrogen oxides. This is a serious pollutant coming from all our cars. Just because air happens to have nitrogen, plays no role in the combustion. We need the oxygen from air. It's freely available. So I just pull in all the air and then start producing this oxides of nitrogen, which is terrible for us. Direct human health impact. Okay, forget CO2, which is a more global climate change impact. This has a direct impact. So can I do something? If I only need the oxygen, can I enrich the oxygen in air by doing something upfront? Obviously, I have to come up with a technology that separates nitrogen out. There is a cost, but then I don't have to deal with things at the end. Okay, there's no NOx to deal with. Also, the carbon dioxide, because there's carbon here, is concentrated. The concentration is much higher in the exhaust, and then it's easier to capture it. So we need to begin to look at these things as a system, look at new ways. So that's why I say you got to look at the entire process and then come up with ways to do it. A lot of research going on in this term oxy-coal combustion. You can use nanotechnology. I won't go into details. There are many pollutants of concern that we need to deal with. Carbon dioxide, once you trap it, you have to sequester it. People are trying to do it geologically, which means buried deep into the ground. Is that safe? Again, imagine the amount of carbon dioxide coming from one plant. I'm going to put it into the ground, deep into the ground. I have to demonstrate this at a large scale. While a lot of people are doing some of this, when we do oil recovery, for example, we pump in liquid carbon dioxide to push the oil out, and the carbon dioxide stays there. We have been producing oil for a long time. So the technology in some sense has been done, but the scale that we are dealing with here is humongous, and we really need to come up with innovations here and see. Can I come up with something better? Can I take the CO2 and convert it to a useful product? People are looking at algal systems. By the way, a plant or a tree takes up carbon dioxide as a resource. With sunlight, produces biomass. Okay, so a tree does it, but it does it awfully slowly. I'm producing 750,000 kilograms of CO2 every hour. I would, all the trees in the globe, even multiplying the numbers, wouldn't take up that much carbon dioxide. So we need to engineer reactors. There are bacteria, there are algae, there are catalytic pathways, there are photocatalytic pathways. Can I use sunlight? Can I bring nanotechnology to bear? It's all of the above. The race is on. People are beginning to look at these things. I'll give you a little more glimpse of what a modern coal-fired power plant should look like. It should be next to a biorefinery. I should be taking up all the carbon dioxide and making it into something useful. Easily said, daunting challenge. Really have to address it. With high concentrations of CO2, as I said, this is geological sequestration. There are many depleted oil and gas reservoirs I can put it in, and the CO2 would be very stable. I've got to make sure it's stable. There's a lot of monitoring that needs to be done. People are talking of deep ocean sequestration, all kinds of sequestration, right? So this is a very important thing. It's beginning to happen. We still have to demonstrate it at a large scale. This is where we need to step up and do some of these things. But more ideal is to take the CO2 and engineer plants. I call these nano or nano-biohybrid systems, which can then make a useful product. And of course, converting it back into a fuel would be the best thing, and then it's a closed loop. I'm just taking this, burning it, let's say, releasing the CO2, capturing all of it, making it back into a fuel, getting the energy out, and recycling all the CO2. So that's, of course, ideal. Many challenges. But let's take a glimpse at a next generation coal-fired power plant. I will use oxygen instead of air. How do I get the oxygen? I need energy to separate it out from air. That energy has to come from the sun, right? Some of these electrolysis is a well-established technology. If I can use sunlight to split water to produce oxygen and hydrogen, I could also directly use sunlight on catalysts to produce oxygen and hydrogen. I can take the hydrogen, make electricity by a gas turbine. I can use the usual oxygen and burn some coal, but then capture all the pollutants, capture all the carbon dioxide. There is some recycle here for the combustion process, but the main thing is either sequester it or convert it to something useful, right? So this is a biorefinery. If I'm looking at some of these techniques, I can make biodiesel. It's a fuel. I can drive my cars with it. And you can begin to see it's going to look like this. So an image of a coal-fired power plant, which is associated with this dirty look. By the way, coal-fired power plants are not like this now. They're very clean, but I just wanted to show that. We are also developing technologies to capture all of these pollutants and then produce all kinds of fuels, even to power aircraft, right? So some of this is beginning to happen in bits and pieces, and we need to do more of it. Okay, so just in summary, coal, very important in St. Louis. need to pay attention, and I won't go through all of this. I talked about it. Let's move on. I told you solar energy is plentiful. Let's look at Thomas Edison quote in the early 1900s. He said that he would put his money on solar energy. Thomas Edison, by the way, inventor of the light bulb, knew the importance of electrical energy. Of course, came by traditional ways of burning oil and coal in the past during his time, but he also looked at the sun. The sun, of course, we know all the advantages. We know some of the challenges. And of course, the sun is intermittent, as we know. The cost, so if I can take sunlight today and make it into electricity, but the cost is about 5 times more than what I have to pay for coal. Now, some people question, is this a true cost? Yeah, this is a market cost. This is what I can buy for. I told you my 100-watt bulb, all I need to pay is 10 cents if I leave it on for 10 hours. If I had it from a photovoltaic system, I would have to pay 5 times more. I would have to pay 50 cents. So significantly more if I start consuming a lot more energy, and one has to then bring this cost down. Okay, now you might question, cost of a renewable is high, but look at the inverse U-shaped curve for a non-renewable source. The consumption rate is exceeding the production rate. So someday we might run out. Nobody is debating where we are. Maybe we are here, maybe we are here, maybe we are here. Depends on the source. Coal, of course, we are way out on the left side, but still it's going to have this kind of a pattern. Someday we might run out. So the cost may be high, but we really need to begin to address this for many of the reasons I also said, and just the amount of energy that I need. So will we run out of fossil fuels? And this is a nice quotation by a sheikh from a Saudi Arabian oil minister in the mid-1970s, when they were floating in oil, probably still floating in oil. The Stone Age did not end for lack of stone, and the oil age will end long before we run out of oil. That's because of the transformational technologies, science coming to play a big role, and all these challenges that are pushing us to do this faster. So this was predicted many years ago. Now, what do we do? These are some things that you can do. Sunlight, remember, is very intermittent. It only shines during the day. I can, however, take that with water, split water to produce hydrogen and oxygen. This becomes an energy carrier now. I can store hydrogen in a bottle, and I can use it at night time to produce electricity, for example. Or I could directly produce electricity. Then I need some kind of battery. I need to charge up my battery and then use my battery at the night time to light up my bulb. So these are all important issues. These are challenges that we face. How you make the device is one very important factor. And we need to come up with new novel materials. These are some pictures taken from my lab that the graduate students, Elijah Timpson and Woo-Jin An, they're making these nanostructured materials, which hopefully could be more efficient, could be readily made in large amounts at a low cost so people can begin to use it. And of course, the synthesis is an important structure. And look at some of these very interesting structures. Once you shine sunlight here, it generates an electron. It's a semiconductor. The electron quickly has to traverse through these columnar structures so that it doesn't get lost, right? If it's lost, if it recombines with a positive charge, then we lose it. So you need to be able to extract it to drive your load. The load is, of course, just a lamp, and you get some kind of work out. So the shape of these materials, the structure of these materials are very important, and we want to do it in a low-cost manner. Then you can take that catalyst, put it in a bath of water, shine light. Here, of course, he's shining UV light, but you could just leave it out in sunlight if this is an effective material, and you begin to produce hydrogen by splitting the water. So sunlight, a catalyst which is reusable, right? So it should be a low-cost device if it lasts a long time, and you can keep reusing it. And then the hydrogen could be used as a fuel in a fuel cell. So a lot of things happening. And some of my colleagues, he's using microorganisms to do this kind of, same kind of hydrogen production, of course, with sunlight. We are using inorganic electrodes. Dewey Holton designs certain materials which will make the light absorption more effective. And then There are also cyanobacteria, which are very good light harvesters and hydrogen producers. So there are many novel things that we need to do. Here are some nanotechnology has a role to play. A simple material is not going to do it. Right now, most of the photovoltaic devices are made out of silicon. The silicon is also used to make microelectronics application chips, which we use in our laptops and cell phones. The cost is very high, and now you're looking at a large area that you want to use. So we need new materials. We need nanocomposites. This is a nanocomposite structure, and he's showing you how he can split water here. You could learn from nature, right? Plants are very good at absorbing sunlight. Could I take out certain parts of the plant or the protein which is effective in light harvesting, or learn from organisms in the deep ocean that are very efficient light harvesters? We call these biomimetic approaches, and then take that and combine it with our engineered system to make structures to do this more effectively at a much faster rate in a stable manner and so forth. So very interesting field. We have to come up with these, as I keep using the word, transformational technologies. While we do it in our little lab, literally the reactors are tiny. Hydrogen is now being used in places like Ireland. They're driving these buses around. So there are, of course, safety issues with hydrogen, but people are beginning to overcome some of these. So this is happening in reality. You could also use hydrogen to tackle the carbon dioxide problem, right? A simple chemical reaction like this. You want to speed it up with a catalyst, right? You could get the hydrogen by splitting water to produce the hydrogen with sunlight, react it with CO2, let's say from a fossil-fired power plant exhaust, get back methane. Methane is natural gas. I can use it again. It'll again produce CO2, and this becomes a closed cycle, right? There already is an infrastructure to use all the methane that we need, even in automobiles in a compressed form. So things like that we need to come up with. Okay, there are challenges. I do want to leave you with the thought that storing the energy as a fuel for use when the sun is down, like right now, photosplitting water to produce hydrogen is one pathway, photoreduction of carbon dioxide is another pathway, and of course designing new batteries so I convert directly to electricity and charge up my batteries. I want to get rid of silicon, very expensive material, keep the silicon for use in our iPods and cell phones and all the fun devices that we have, but then come up with new novel materials. The overall efficiency, which I've really not mentioned in detail here, is very important, because if I don't have a high conversion efficiency, I need to cover up a large area. Compared to coal, which is a dense fuel, I don't need as much area, and I'll try to show you another set of graphs which show that. So that brings me to what are we doing at Washington University. We have this center which coordinates ICARES, which coordinates energy and environmental efforts across all our 7 schools. This is such a topical area. None of our schools is ignoring it. We are all working together. We not only have all our 7 schools active, we are reaching out to 25 other universities all across the globe. It's a global challenge problem. We don't want to be sitting here in a corner in St. Louis. It'll be impossible to solve the problems of the world. So we really need to partner, and this has been very exciting. And then there are several departments. And then do I want to step up and really begin to demonstrate some of these technologies? A lot of talk. You will say it costs a lot of money, but should I do that? So let's keep that in mind and see how we do that. This is McGeep. I'll sort of skip some of these. A lot of activity with international symposia. Go to this website, mcgeep.woostel.edu. You'll see a lot of exciting things happening, research projects, educational projects. There's a lot of educational things. Departments like this, my own department, where we have 70 doctoral students going at it, looking at different things, different issues related to energy and environment. And I'm breezing through some of these. But let's talk about the Consortium for Clean Coal Utilization. We've just established this on campus. There are a lot of things, of course, research, technology development with industry support is an important element. So is education. but let's talk about this clean energy research plant. Can my coal-fired power plant look as clean and have zero emissions? Can I do that, right? So we want to develop facilities at Washington University. St. Louis is a region for clean coal research and development. There's a lot of talk. You'll hear there's a lot of coal reserves in Illinois, and there are going to be some demonstration facilities that are probably going to get approval soon. We want it to be zero emissions. If I want to demonstrate something on campus, I want to make sure it's zero emissions. And I want to then develop technologies and literally look at global scale implementation, starting, of course, on a small campus. So let's look at our campus. This is my last sort of topic. A beautiful campus doesn't look as beautiful on this map. This is Forest Parkway. We are somewhere here at the zoo, so you can drive down. This is our new building coming up, by the way. It's an energy efficient building. I didn't talk about energy efficiency. Not a drop of rainwater is going to go into the sewer. So it's going to be a very fascinating thing on the prime corner of campus. But this is a beautiful campus. I want to look at our students who sort of live here. They call it South 40, and they consume 5 megawatts, only 5 megawatts. Remember, a light bulb, 100 watts, 5 megawatts, still a large amount, right? We have about 6,000 students. I think 3,000 live here. But the area of a clean coal plant that I need would be 2,500 square meters. So you can imagine 50 meters by 50 meters, right? And I look, where do I have space on this dense campus, beautiful campus, don't want to break down any buildings. Hey, here's a play field, let's try to take that up, okay? And we'll do that. It's next to the dorms. We want our energy production next to where it's being used. And you can see, I can literally build one there. And if it's zero emissions, that's what I want it to be. Zero emissions. In fact, I call it negative carbon emissions. There are some techniques we are going to use where we actually remove carbon dioxide from the air. It's a big challenge. It's not cost effective. It's not going to be seen all over the St. Louis region. But this, we want to just demonstrate this for our campus. Okay, someone comes and says, why are you talking about coal? Let's do everything with sunlight, right? Let's see if that is possible. For sunlight, I now need a 50,000 square meter area. That's current technology. The efficiencies are low. And if I really want to do it, I can do it, but I need this much area. So let's see what that refers to. Again, our beautiful campus. Keep in mind, this is where we are going to be and doing a lot of research inside this new building. The whole campus gets covered up, right? I'm even including Brookings Hall, where our chancellor's office is. So, and he's a solar energy expert in his heydays. So, but we can't do that. It's impractical, right? I can't cover up. In fact, the dorms are gone too. Where will the students live? We might have the energy. So, and this is under idealized conditions. Like when the sun sets, I'm not going to be producing this 5 megawatts that I might be needing at nighttime. I will need battery technology. So, you know, it's impractical. But that doesn't mean we don't do it. But we just have to understand what it's going to take. Then comes, hey, let's use windmills. Look at the amount of area I need. St. Louis, the wind doesn't blow as much. And we might see a windmill here and there. That's great. Good educational value. But I want to power and get 5 megawatts. Again, our beautiful campus. Now, some of you might live in Clayton and U-City and Ladue. All of it is gone, okay? It's all windmills. In fact, you begin to see mountains. So the question comes up, where is Washington University, right? Where's my wonderful building where I want to do research and solve the problems of the world? So very impractical, but what does all this mean, right? Why am I showing you this? Let's go back to the solar thing. I do not have enough space on my campus, that's for sure, but do I have it elsewhere, right? And I need a smart grid then, because if I do it elsewhere, I need to transfer or transport the electricity. You'll hear a lot about the smart grid. It has to be smart, and it has to have storage built into it, right? And of course, I look at Nevada. What's Nevada? All desert, a lot of sunshine, and maybe casinos. We can get rid of both in one shot. And that's my yellow area that I need. So you might say, hey, we are in St. Louis. Let's use up Nevada and put up these solar plants and produce all the electricity we need right now, today, in the United States. Of course, they might complain somewhat, but look at the magnitude. It's only 25% of the area covered by roads, right? We have built roads all over the United States. We have done this. Of course, I need a new material, I need a better efficiency, but we can do it. So it's not surmountable. You need some transformational developments, but we need to begin to think about this. So while I can do it, we need to keep the bigger picture in mind as we go along. And there are many associated issues. So even if I want to do it there today, I can't. There are many challenges. There's a cost factor involved. All of this has to be brought down. Okay, I want to take care of the entire world. I give up Colorado, my geography, of course. I guess Arizona, New Mexico, and what's the other state? The fourth state around it. We give it up. We can produce the entire world's needs. Remember that 170,000 terawatts. Obviously, I need to store it. I need to transport it maybe to Africa. Very difficult to do that. Maybe I can make enough hydrogen to take care of it, but we need to make these beginnings. So it's promising, a tremendous challenge, but could be overcome. There is a role for policy. I didn't even get into it, but we need policy to promote this, right? We need to do it for fossil fuels. We need to bring in conservation and efficiency improvement. As I said, shift the United States towards the left. We don't need to consume as much or waste as much is the right term. Maybe we want to consume what we need to lead a good quality of life, but we don't need to waste as much. We need to develop sustainable energy sources. Sustainable meaning right from the entire place we get the fuel all the way to the end usage, right, the entire life cycle. And keep in mind this global climate change. It's a daunting problem. We need to also learn how to adapt to it. Maybe adaptation needs to come in. So all of this policy has to play a role. So let me summarize now. And energy issues of global importance. Hope I could convey that. We need global collaboration to solve it. In addition to that, we want to promote sustainability. Each of us individually has to take some steps. We have to conserve wherever we can, especially we here in the United States. And this, of course, brings up this tremendous quotation. There is enough on this earth to meet every man's need, but not enough to meet every man's greed. So very profound statements, so very applicable to the energy sector. And I think it's a promising future. Scientists are stepping up to the challenge. Washington University, in its small way, is doing it. And with that, I'll thank you for your attention. I'll be happy to answer questions. We are developing tomorrow's solutions. If people are interested in this, every first Wednesday of the month, we meet informally and have a discussion at the Danforth University Center, room 276. Anyone is welcome. And of course, I would like to thank my own doctoral students who are also tackling these problems and will come up with solutions to some of these challenges that I talked about. The websites are also informative. And with that, I'll pause and answer any questions you might have. Thanks. You had a question, yes. Right, so gas hydrates are, I think, these methane hydrates. As I said, it's going to be a mixed portfolio. Clearly, in this 1 hour or 45 minutes or what time I took, I can't address every source. There are these gas hydrates, which is a potential source. There are many challenges. There are many issues associated with that, but it's one of the things in that mixed portfolio. I also feel there's a lot of research that needs to be done. I'm not an expert personally on this field, but clearly it has a role to play. And the message here, of course, is everything has to be brought to bear. And the end point, while we want to be completely sustainable, how we get to that end point, what that end point would be, is still an open game. So I would say all of the above. And we don't want to rule out anything, and every resource and methodology has to be explored. Okay. Yes. Right. Correct. So of course the answer remains the same. It's all of the above. In the United States, we have lost our manpower and expertise in the nuclear field. So that again becomes, at least in the educational sector, right, because of all the policy moves, the environmental activism, some rightfully so. So there are scientific and technological issues that we have to meet. So clearly nuclear has to be a role. 30% of, I mentioned about 70% of our electricity in Missouri comes from coal. Other 30% is from nuclear. So we are doing it today. We need to maybe do more, but I wanted you to, that's not the only solution again, right? If I want to get my 16 terawatts from a nuclear plant would be about a gigawatt each. It's daunting. I have to make one every other day, literally. So getting all the licenses for a nuclear plant, we need to speed it up. We need to make sure the safety issues are important. The energy security from a negative sense now becomes important too. Proliferation is an important issue. Of course, I might do it in the United States, but United States should also be a leader, a global leader. We are the technological leaders, have been. We should continue doing that. So if we say that nuclear should be proliferated to meet Africa's energy needs, the issue of security in a negative sense becomes important. Can you begin to concentrate and make weapons-grade material? These are also important issues. So I feel nuclear is not going to be as prominent. This is now me speaking as an individual, but it has to play a role again in that mixed portfolio. Okay. Yes.
Burning 1 unit of coal
Mm-hmm.
several times that amount of CO2.
Yes. Okay, so let's say I have the best coal, then it's pure carbon. Obviously, coal has a lot of other literally junk in it, but coal is carbon. So I take 1 mole of carbon. Now this is my chemistry lesson here. 1 mole of carbon reacts with 1 mole of oxygen, which is O2, to give me 1 mole of CO2, correct? If I burn it completely. Carbon has a certain weight. It's the atomic weight is 12. Oxygen is 32, right? So CO2, because mass has to be conserved, CO2 is 44. So 12 grams of carbon give me 44 grams of carbon dioxide. So that's 3 point something times. So every gram of carbon or mass of carbon is giving 3.7 times the amount of CO2, right? So 200,000 kilograms of coal is equivalent to close to 750,000 kilograms of CO2. So it's just the mass balance because I'm tagging the oxygen. It's a heavier material per mole basis, on a mole basis. Yep. Mm-hmm. Excuse me? Oh, sorry, this disappeared. It's at 4 p.m. It's at 4 p.m. We meet at 4 p.m. The meeting goes on till about 6. We pick on somebody to give an informal, thought-provoking presentation for about 20 minutes, 30 minutes, and then students love pizza and pop. That comes in, so you get free pizza and pop, and then we solve the problems of the world collectively. So it's 4 p.m. at the Danforth University Center, goes along till about 5:30, 6 p.m. Okay, this is our new building on campus, Danforth. Should I go back to the map? No, that's a very complex map. It's on which side of, do you know any building on campus? Okay, physics is a little removed. In the center of campus is Graham Chapel. Right opposite Graham Chapel is the Danforth University Center. It's a new building. There's a parking lot below it. And at that time, I think you can, it's close to the greenhouse. It's along that road, but a little further on towards the gymnasium. So it's a new building. If you come to campus and ask anyone, they also call it DUC, D-U-C. So you can ask them where the duck is, and they'll send you there. Someone else had a question here? Yes, please.
You talked about some potential processes where CO2 could be converted to useful fuel source and like that into the beginning and become a closed-loop system.
Mm-hmm.
Doesn't that sound just a little bit like perpetual motion?
It's not really. There is if I say that no energy input is needed, that would be true. So here I said I need tremendous amount of energy, at least with today's methodologies. The energy has to come from the sun, ideally. So that was, it's a very quick talk. I'm covering a lot of aspects. So I need to pump in tremendous amount of energy to do that, right? To convert it back. But I'm telling you that the sun is providing us plentiful energy. In fact, the trees do exactly that. They take CO2, they take sunlight, and they make biomass, which I could burn, right? Wood, which I could burn, and which we do burn, but it's too slow a process. So we have to speed that up. We have to get energy from a clean source. We might use the energy to make hydrogen, which will help me do that conversion. So there is a significant energy input into the process. Obviously, getting it from the sun would be great. But these are, correct. And everything comes at a price and a cost. And we have to understand all the pathways. Yep.
A lot of times when people talk about CO2 sequestration
Mm-hmm.
or taking care of CO2, they talk about photosynthesis or converting CO2 back into a carbon-based fossil fuel,
Right.
which is really great. It does solve a lot of problems, but it's kind of it's more solar energy powered, and it really helps and whatnot. But are there methods out there of collecting CO2 that don't involve solar energy?
Okay, so you mean, so the question is, can I convert CO2 without using energy? And that is very difficult because that's a stable form of carbon going to carbon dioxide, right? It's a stable state, and I have to reduce that. So whenever I want to make it, let's say I want to make it back into carbon, I have to get the oxygen out. And it's thermodynamically impossible to do that. So I have to really pump in energy to make that happen, to make it go the other way. When we undergo photosynthesis, you use the right term, which happens in a tree and a plant. It's getting it from sunlight, and that's the photosynthesis, but it's a very slow process. So what we are trying to do is learn from those processes and engineer it and do artificial photosynthesis. But there has to be an energy input. Otherwise, you'll begin to question my basic thermodynamics and things like, he mentioned perpetual motion. So this, of course, we can't ignore that fact. So we do need an energy infusion to make this happen. And there's no way around it. You could, of course, bottle up the CO2. When we do geological sequestration, you're bottling it up deep. You, of course, need some energy to push it deep down, but much less than what we need to convert all of it. So these are all important issues. They all have to play a role. We have to do the calculations, and again, different technologies and methods will win out. Cost is an important issue, so that is linked to the energy consumed. Okay, yes, please. Correct. Yeah, the tides. So if one looks at all these renewable energies, you can point it back to the sun somehow, right? The tides are formed again due to the motion of the earth and temperature differences sometimes and so forth. Wind is that way too. So certain parts of the globe, tidal energy is important, especially in the coastal regions, and but it's not as significant in terms of the magnitudes that I mentioned. It's also localized, so you'll have to extract that energy, convert it, and there are turbines to do that. And there are people like off the coast of Taiwan, for example. The tides are very favorable, so they are planning to set up some tidal power plants. And Taiwan is a small country off the coast. I mean, China's on the other side, a humongous nation consuming a lot of energy, but maybe a fraction of Taiwan's energy needs could be met by tidal energy. So people are doing a lot of this work. Of course, in St. Louis, we are landlocked, so there are other approaches that we have to look at. Mm-hmm. Yes? Right. So right. So water, of course, is again a very stable compound, and that's what I was trying to show you. You take the sunlight and you take a catalyst and you split the water to get hydrogen. So water becomes a fuel now, a resource, an input, a reactant to give us the hydrogen, right? And there's a lot of water on this globe in terms of the amount of hydrogen that we need, so that's a feasible pathway. But water itself cannot be used. The water has to be split into hydrogen. When you split it, you also get oxygen. So the hydrogen you can then use as an energy carrier. So that's what I mentioned, and many people are looking towards that. There are still many challenges and many issues with that, right? Right, so you have ample resource. It's a benign resource, but you need the technology to split the water, right? Or I need, again, the energy. So if I need energy to split water and I'm getting it the good old-fashioned way by dumping a lot of carbon dioxide, then that's not the right pathway. So I need to use sunlight. I need to come up with new methodologies to get that energy to split the water. Of course, you could use nuclear energy to produce electricity and then electrolyze water. So many people are proposing things, but a solar pathway is probably the most attractive. Mm-hmm.
In these models, I guess the driving force is the number of people and the human development factor, how much they'll use. So on the demand side, how many people,
Mm-hmm.
how much they'll use 6,000 watts per liter per capita, whatever.
Mm-hmm.
Isn't there some point where sustainability will say that you can't handle more than you're showing like 12 billion people? We're going to run out of some other resource, more energy. Is clean water. You said we've got plenty of clean water. Clean water is going to take more energy.
Right.
Or new technology there to supply 12 billion people.
Correct. So these are all very important points. We have to eventually begin to control the population. I cannot maybe then maintain my standard of living uniformly. Those are, in some sense, myths. There will be differences which then lead to instabilities and so forth. So we have to really begin to address this. So it's a complex problem, but 12 billion, those are realistic estimates, very realistic. We are going to be facing those challenges 40 years, 30 years down the road. And people feel those could be surmounted, but you just can't keep going. There's some very neat, in fact, I also have it if you want to see. I hope I have it. Yeah, how many planets do I need, right, to support everyone? So even today, I need 1.25. Who's going to give me this planet? We don't have it, right? And then how many do I need to support everyone at current standards? If the population doubled, I need 2.5, right? We just have 1. And then look at this, support the current population at standard of developing countries, 3. So while I say technology is great, will come up, there's always a limit. And we need to address those issues too, because these are realistic. 6 planets. Of course, I can go explore space, find the other 5, but that's a daunting task too. So this is important also. But the projections are very realistic, and we feel we can tackle some of that, but you're right. Some stage